All right, I'm sorry. I think, okay, let's resume. So take a look at what we have here. We have some function, the graph of some function, and my question is this function differentiable at that sharp corner you see up there, right? Is it differentiable at uppercase A, that point? Or is it differentiable at an x value of 0? Maybe I could put it that way, right? You may say, well, what's the problem? Let me tell you. The problem is, if we try to draw a tangent, how should you draw a tangent? Please be careful about, let me put it this way. You probably thought, quite rightfully, that when I showed you how to draw a tangent by picking secant lines and bringing the point closer and closer and then saying that the tangent line is the limit of the secant lines, you may have like, oh man, that's an overkill. But you will now see why that is not an overkill. Okay, check this out. So to draw a tangent at a point A, what should I do? I should pick a point to the right of it first and draw a secant line passing through those 2 points, right? And then what should I do? I should try to bring this point B closer and closer, and each time I need to be drawing the secant lines. But GeoGebra, this software makes life easy in that regard, so all I need to do is just change the value. So you can think of it as I'm drawing a whole bunch of secant lines, right? So notice, as I'm doing this, the secant lines, as I'm letting B get closer and closer to A from the right, the secant lines are approaching this particular line. And now that is the tangent line. What is it? Well, at least that is the tangent line based on the points to the right. Can you remember this tangent line, please? Look at how it's oriented. It's leaning back on the top. It's leaning back like a reclining seat. Remember that. Now, the thing is, we should be able to draw the tangent by actually picking points to the left of A and then looking at the limit of the secant lines. So let me attempt to do that now. So starting at left, as I let B get closer and closer to A from the left, now we got this to be the tangent line. Aha. So which one is the tangent line? Which way is the tangent line leaning? There is an ambiguity, right? We cannot be really sure about which way it is leaning. Is it leaning forward like here? Or is it leaning backward like there? Right? That ambiguity is a problem. Why is that a problem? Now if I say, what is the slope of the tangent? Should you give me this slope based on the points to the right? Or should you give me the slope based on the points to the left? There is a confusion. Or there is an ambiguity, especially. And that's why we say the function is not differentiable at a sharp corner. Cool? It is for this reason. Slopes of tangents drawn based on points to the right and points to the left are different. They have different slopes. Cool? That is one way a function would not be differentiable. Let me look at another way the function wouldn't be differentiable. Why are you? Okay. So this is the graph of function. Once again, my question is the function differentiable at A? What do I need to do? I need to draw a tangent and look at what the slope of the tangent is at that point, and I'm done. Right? Again, let's embark on that process of, okay, pick a point to the right, and then draw a secant line, and then bring this point closer and closer, right? Let's do that. Now look at the slope of look at the tangent line. It's getting more and more, what? Vertical. It's getting closer and closer to being really vertical. And in fact, well, if I just come, it is vertical. What's the slope of a vertical line? There is some rise, but the run is 0. If you have a vertical line, the slope is undefined because there is some rise, but there is no run. Run is 0. You are dividing by 0, rise over run. So vertical tangents, vertical lines, in fact, do not have any slope. Its slope is undefined, right? And because of that, we have a problem. So when would a function be not differentiable? What would be another situation where a function would not be differentiable? When the tangent is vertical. That's the point I want to make. Cool. A third scenario, non-differentiable 3. Check this out. Suppose I have a graph of a function that looked like this. Let me ask you, is this function continuous at A? What's continuity? Limit of f of x as x approaches A must be equal to f of A. Right? Remember that, recall that. Limit of f of x as x approaches A is equal to f of A. When that happens, we say the function is continuous at A. Now, at x equal to 0, I'm asking, is this function continuous? What is the limit as x approaches 0 from the left? 0.5. What's the limit of f of x as x approaches 0 from the right? 1. Is 0.5 equal to 1? No. So what's the limit? Limit of this function is undefined. Limit does not exist at x equal to 0. Right? So if limit does not even exist, obviously we have to say the function is discontinuous. And also, do we know what kind of a discontinuity this is? Well, it's a jump discontinuity because the function's value jumped from 0.5 to 1 pretty much at the same spot at x equal to 0. Pretty much. Right? Okay. So what? The function is not continuous. Does that mean automatically that the function is not differentiable? That's what we are trying to find. Once again, if we adopt this strategy of drawing a secant line, now notice what am I doing? If I want to draw the tangent line at 0, at x equal to 0, well, I put a solid dot here as to indicate that at x equal to 0, the function has a value of 0.5. So that's where I need to have my point, my left point A, and the other point B, I take it to the right of x equal to 0. And when I do that, and I do my thing, bringing B closer and closer, now the problem is this tangent is getting vertical, right? So based on the points to the right, the tangent is vertical, and that's a problem. Is that the same problem if we were to let this approach from the left? No. When we let this other point B approach from the left, we have secant lines like this. then that doesn't seem to be a problem. In the sense, the tangent is nicely defined. It's got a nice slope to it. But it's the right side that created a problem. And so once again, because the two tangents are not the same, the left tangent and the right tangent are not the same, the function is not even differentiable there. So that could happen. Next, I know this is all, man, what's up there, man? This is all a whole bunch of theory stuff. Yeah, it is. You must know this. It'll help you a lot, let me tell you. When you take physics, they expect you to draw curves of, they'll give you the derivative curve. And then they'll say, draw the function curve itself. Or they'll give you the function curve and say, draw the derivative curve based on this one. Why is that? That's because they'll say something like, hey, if something is moving along a straight line, then its position and its speed, they are the derivatives. The derivative of the speed is the position. The derivative of the position gives you the speed. So you need to know how to go from the speed curve to the position curve, and the position curve to the speed curve. That means a function curve to the derivative curve. You must know all of that. So please pay attention and try to clearly understand all of this stuff. Okay, here is my fourth scenario. Do you see that itty bitty hole in the graph? Right? I wish I could make it bigger, but looks like I can't. Okay, so there is a hole in the graph. Obviously, that's where I'm interested in. Is this function differentiable at that point? Well, for that, let's recall what the definition of the derivative at a point is. F prime of a, the derivative of function f at point A, is limit of f of a plus h minus f of a over h as h approaches 0. Based on this, I want to say, in that case, this function is not differentiable at this x equals a. A is 1 here. Why? Can you pause the video and think about it and tell me? My question is, this function, is it differentiable at this hole? And I'm expecting you to answer that based on this definition of a derivative at a point. The answer is no, the function is not differentiable, because notice in the definition you have to have f of a. What is f of 1? There's a hole in the graph. There is no value, man. So whenever there is a removable discontinuity, then the function is not differentiable. In fact, did we see an infinite discontinuity? Right? When the slope is the vertical, when we had a vertical tangent, and we saw a jump discontinuity, and now we are seeing a removable discontinuity. The moment there is a discontinuity in the function of whatever kind, the function is not differentiable at that point. That is the point that I'm trying to drive at. That is one of the reasons. A sharp corner is another reason why a function wouldn't be differentiable. And other than that, these are the scenarios. Cool? When the tangent line is vertical, when there is a jump discontinuity of this kind, or when the function is undefined, there's a hole in the graph, function is not differentiable at those points. Okay? Now, here is a theorem. Are you ready? You really have to pay attention now. What was the very first thing I covered in this course, folks? You remember? The very first lesson is about logic. What did I say when I covered logic? I said, you really need to understand logic because especially this conditional and the converse and contrapositive, that stuff, those three things you really need to understand. And I said because every theorem is in the form of a conditional, just about. If it is not in the form of a conditional, if P then Q, we can always write it in that fashion. So now notice, if F is differentiable at A, then F is continuous at A. Cool? If F is differentiable at A, then F is continuous at A. That's a theorem. Is this in the form of a conditional if P then Q? Yes, it is. And is the theorem true? Oh, obviously. You wouldn't call something as a theorem if it is not true. So somebody must have had an irrefutable proof that this is true. And so let's take it to the bank. We are not going to prove this. That's at a higher level, but we'll take this to be true. If F is differentiable at A, then F is continuous at A. And then I asked you to do something. The moment you see a theorem, come up with what the converse of this theorem is. Immediately, what is the converse of the theorem? And then ask, is the converse true? And also, figure out what the contrapositive is. And is the contrapositive true? Well, the contrapositive is automatically true when the conditional is true. So now ask yourself, what are the implications of the fact that the contrapositive is true? What does it mean the contrapositive is true? That's the key. Cool? So what's the converse of this? If P then Q. The converse is if Q then P. So what should the converse of this be? P is F is differentiable at A. What is that? Pay attention. P is F is differentiable at A. Q is F is continuous at A. Okay. So all we need to do is now state this if Q then P. So converse would be if F is continuous at A, then F is differentiable at A. That is the converse of the theorem. Is that true or false? F is continuous at A, then F is differentiable at A. I don't know, man. Here is the idea. To be able to answer this question, you need to ask, can you come up with one counterexample by some chance? If you can, your work is done. You can clearly show that you can give me that counterexample and say this is false. So let me in fact go ahead and tell you this is false because there is a counterexample. Can you tell me what that counterexample is? You have in fact seen that such a counterexample. What is that counterexample? It is such a way that F is actually continuous at a certain point, but the function is not differentiable at that point. Let me repeat that. The counterexample is such that F is actually continuous at a point A, but it is not differentiable at that point. Do we have a function like that? Have you seen a case like that? Yes, we did. Which one? That one with the kink. I didn't say, oh, come on, Sammy. Oh, no. Right? That is false based on that kink one. There is a sharp corner. that function is clearly continuous at 0, but it is not differentiable at 0. Oh, I do have a counterexample. What am I talking about? Absolute value function y equals absolute value of x at x equal to 0. Why is that? Isn't absolute value of x, do I have a graph of it or not? Oh, brother. Does absolute value graph have a sharp corner, folks? Yes, Sammy. I cannot draw, man. The screen is sitting vertical, and now I have to. Okay. Close enough for government work. Let's say this is the absolute value. Of course, it won't be curving like that. It's a straight line. Both of them are straight lines. So here at this x equal to 0, isn't that continuous but not differentiable, sharp corner? That's the idea. So that's a counter example. And so we have to say the converse of the theorem is false. However, what is the contrapositive of the theorem? Right? What is the contrapositive of if P then Q? If not Q, then not P. Not, this part is P, this is Q originally. So we need to come up with not Q, negation of this second part, then not P, negation of the first part. So if F is not continuous at A, then F is not differentiable at A. Would you agree that should be the contrapositive? Cool. Is the contrapositive true or false? I just reminded you. Automatically true. Now let's look at what the implication of that is. If F is not continuous at A, guess what? Automatically F is not differentiable at A. You can take this to the bank. It's a very, very, very powerful result. The moment you find that a function is not continuous at a point, you can be guaranteed that function is not going to be differentiable at that point. That is precisely what we saw in the past few slides. Wherever there was a discontinuity, clearly the function was not differentiable at that point. Well, even if it is continuous, automatically didn't mean that the function was differentiable, like in the case of sharp corners absolute values. But if there were to be a discontinuity, you could be guaranteed the function is not differentiable there. Please allow me to repeat that and clearly have it in your head. If a function is continuous, does not automatically mean the function is differentiable. No, it doesn't. However, if a function is not continuous at a point, automatically the function is not differentiable at that point. Cool? All right. Earlier discussion about not, yeah, okay. Now, can we find f prime of x given f of x equals 3x cubed minus 2x? This should be fairly straightforward, especially considering what we did in the previous section. We had the same function. We were supposed to find f prime of a. But now I'm asking find f prime of x. The only difference is instead of a, we have an x. So the whole thing is identical to that. And I pretty much, I'll tell you, when I made this PowerPoint, I just copied that and changed x's to a's to x's. That's it. And so you go through this whole process. Earlier, I think we got 9a square minus 2 to be the value, the final answer. Now you will get 9x square minus 2. Okay. So there is nothing new from my side that I need to teach. Just because there's only one example here doesn't mean, I won't ask any questions on this one. I will. But there is nothing from my side that I need to teach. You just need to figure out these kinds of limits. Especially look at, why don't you do this? Go back to the previous section, and in every one of those problems, instead of finding f prime of a, change it to finding f prime of x. And the approach would be just like this one. Cool? All right. Oh, I already did that for you? Man, look at this. We needed to find f prime of a, and I just copied that one and said, okay, let me make it f prime of x. And what did I do? The same thing that I did there. Multiplied by the conjugate and so on. Right? And this turns out to be 2 over, instead of 2 over 1 minus a, the quantity raised to 3 halves, we have 2 over 1 minus x, the quantity raised to 3 halves. Cool? Okay. Quite interestingly, there are many other ways of stating the derivative. Yeah, please be familiar with all these ways. For some reason, calculus, Leibniz and Newton, they both came up with calculus, but they used different notation. Leibniz is the one who used this limit concept, limit as, and also f prime and all that. Or no, Leibniz came up with this dy dx way of writing things. F prime of x is the same as y prime, if y equals f of x. And that y prime is the same as dy over dx. But people don't read this as dy over dx for some reason in America. They just say dy dx. They do not mean dy times dx. They actually mean dy over dx. And that is the same as ddx of y. Some people use this differential operator called d or d sub x to indicate I'm differentiating with respect to x. So you can kind of forget these two. The last two you can forget. But you definitely need to be familiar with f prime of x is the same as y prime. It's the same as dy dx, and that is in turn the same as ddx of y. And in fact, this is the one that I prefer a lot. Find a ddx of something is how I would like to state that. There are many advantages to that, and that's why I do that. Cool? All right. That helps us to talk about what are called higher order derivatives. What do I mean by that? If I have a function f, can I take the derivative once and come up with a function called f prime? Let me repeat that. If I have a function f, can I find its derivative function f prime? Yes. So now what is f prime? F prime is a function, some kind of a function. Well, if that is the case, can you find the derivative of the derivative? Yeah, of course. If the function f prime is differentiable, you can differentiate it again and find its derivative. Whoa, what is that called, man? That is the second derivative. F prime is the first derivative, and this derivative of that is the second derivative. Okay, so that's what I'm stating here. If y prime equals dy dx is thought of as the first derivative, then taking the derivative of the first derivative yields the second derivative, and the way we denote that is y double prime, right, 2 primes, or d square y dx square. Notice how I read this. D square y over dx square, but I didn't say over. Just like that dy dx, people say, they say d square y dx square. But you kind of have to understand, oh, you mean d square y over dx square. Yes. Cool? All right. So what is f double prime of x, folks? That's the same as y double prime. And that's the same as d square y dx square. What in the world is d square y dx square? That is d dx of dy dx. What? Yep. Now check this out. Let's go back to this one. What is dy dx? Isn't that d dx of y? In the same way, d square y dx square is d dx of dy dx. So this is as simple as this. If you are given a y, how do you find the second derivative? First find the first derivative dy dx. And then find the derivative of whatever you got with respect to x again. D dx of what you got. That's how you find the second derivative. Cool. And we can talk about f triple prime of x, f to the fourth prime, fifth prime. You can keep on doing that. Okay. In general, f to the n of x, when you write, you have to enclose that n in parentheses like that to indicate we are taking the nth derivative. That is the same as d to the n y dx to the n. You differentiate y n number of times. You differentiate f of x n number of times. That's the idea. Cool? All right. So that's the end of this section. And sorry about the mishap. I'll post them as part 1 and part 2.